Today, all, welcome back to this course. Today, we'll be looking at Module 2, Simple Linear Regression, looking in depth into this. By way of module objectives, by the end of this module, we'll explain what regression analysis is and why it's useful. We'll state and interpret the simple linear regression model, including the roles of dependent variable, independent, and error term. We'll derive and compute the OLS estimator for intercept and slope, and explain why OLS chooses the best fitting line. We'll state the classical OLS assumptions and explain their economic meaning and why they matter for interpretation and inference. We'll interpret regression coefficients in economic terms. We'll also compute and interpret goodness of fit measures, such as the R squared, adjusted R squared, and their limitations. We also apply simple regression to realistic economic examples. By way of introduction, regression analysis is a core tool in econometrics because it turns economic ideas into measurable statements that can be tested with data. Economists frequently propose relationships as consumption rises with incomes, demand falls when price increase, or education raises wages. These claims are meaningful only when we can quantify them. By how much does consumption change when income changes? Does relationship hold after accounting for random shocks and differences across individual firms or time? Regression provides a structured answer by fitting a model that links an outcome variable to an explanatory variable and separating systematic patterns from random variations. In applied economics, the regression serves at least four practical purposes. First, it estimates the magnitude of economic relationships. Second, it tests hypotheses derived from theory. Third, it supports forecasting by using estimated relationships to predict outcomes or new values of explanatory variables. Fourth, it provides evidence for policy analysis, such as evaluating how a change in interest might affect investment or how a subsidy might change consumption patterns. Simple linear regression is the starting point for this entire family of methods. It studies the relationship between one dependent variable and one independent variable. With real economic problems, while real economic problems involve many variables, understanding SLR is essential because of the logic of estimation, interpretation, uncertainty, and model evaluation in multiple regression built directly on it. In this module, we learn how the model is set up, how parameters are estimated using OLS, how to interpret the estimated coefficient as economic quantities, and how to judge whether the model fits the data well. Why regression analysis matters in economics. Regression analysis is the primary empirical tool used in applied economics. It allows economists to move from qualitative theoretical statements to quantitative testable relationships. So regression establishes relationship between X and Y. Economic theory often proposes directional relationships such as consumption and all. Regression quantifies these relationships, said that before. The central question is not merely whether two variables move together, but how much, under what assumptions, and with what degree of uncertainty. Let's look at the role of simple linear regression, SLR. Simple linear regression studies the relationship between one dependent variable and one independent variable. Although real-world economic problems often involve multiple variables, understanding this is essential because the next one, which we are going to talk about, which is multiple regression, builds directly on this simple logic. SLR introduced the idea of estimation, uncertainty, assumption, interpretation, and model evaluation. Let's look at the population that is the true regression model. This is the equation. This equation represents the true but unknown relationship in the population. Now, under this simple linear regression, there are two. We have the population like this one. B0 and B1 are fixed but unknown parameters that describe the systematic part of the relationship between X and Y. The error term U captures all other determinants of Y. that are not included explicitly in the model. Now let's look at the sample regression model. This is the second one. This is the equation. Because the true parameters B0 and B1 are unknown, we estimate them using sample data. Because they are unknown, we draw them from the population. B0 and B1 are numeric estimates computed from observed data. The difference between Y and the predicted Y is called the residual. So what you predicted and what you get, the difference between it is called the residual when you estimate. We looked at dependent variable before. We'll just talk it again briefly. Dependent variable is the outcome we aim to explain or predict. Example include consumption and others. So careful measurement of Y is crucial because measurement error increases noise and reduces precision. The independent variable X explains the variation in Y. In SNRO, interpretation is clean because there's only one X exactly. That's why it's simple. Then let's look at the intercepts, B0 and B1. B0 is the expected value of Y when X is 0. Its economic meaning depends on whether X equals to 0 is realistic. B1 is the marginal effect. It measures how much Y changes on average because when X increases by 1 more unit. Right? The unit matters. If Y is measured in naira and X in years, B1 is naira per year. That is the marginal effect. Now let's look at ordinary least square objective, OLS. This is the equation for OLS to calculate OLS. OLS chooses the line that minimizes the sum of squared residuals. I already told you what a residual is. The difference between what you estimated and what you got. Squaring residuals ensures positive and negative errors do not cancel out. Large errors are penalized more heavily than small ones. OLS estimators. We have closed form solutions. This is the equation. The slope is the ratio of covariance between X and Y to the variance of X. If X and Y move together strongly, the covariance is large and the slope is large. If X varies little in the sample, the slope estimate becomes unstable. Let's look at key algebraic properties of OLS. We have the regression line passes through the sample point. The sum of the residuals equals 0. The residuals are orthogonal with that is uncorrelated with X. The predicted values and residuals are uncorrelated with sample. Let's look at some of the assumptions. Assumption 1, there's linearity in parameters. That is, the model must be linear in B0 and B1 must be straight. There must not be, it must be equal to the power of 1. That's what linearity means. This does not require Y to be linear in X in every sense. Transformation in lin-X are allowed. Linearity in parameters ensure OLS formulas are valid. Assumption 2, random sampling. It is taken that the observation must be randomly drawn from the population. Random sampling ensures representative and supports probability-based inference. Non-random samples may introduce selection bias. Assumption 3, there is variation in X. X must vary in the sample. If all observations have identical X values, the slope cannot be estimated. Mathematically, this equation must be greater than 0. That is, the summation of X minus X squared must be greater than 0. Assumption 4, there is 0 conditional mean, that is exogeneity. This means the error term is unrelated to X on average. This is the most important assumption for casual interpretation. If this is violated, OLS estimates may be biased and inconsistent. Assumption 4, homoscedasticity. This is assumed that there is homoscedasticity. The variance of the error term is constant across values of X. If errodacity exists, OLS coefficients remain unbiased, but standard errors become unreliable. Robust standard errors can correct inference under heterodacity. Let's look at the sixth assumption. No autocorrelation. Error terms should not be correlated across observations. This is especially important in time series data. Autocorrelation distorts standard errors and hypothesis testing. Let's look at variance and standard error of B1. Right? This is the equation. The precision of the slope estimate depends on the error variance and variation in X. Greater variation in X leads to more precise estimates. This is variance is estimated using residuals. I already explained what residual is. Now let's look at the test for slope. T is equals to B1 minus 0 and all. This is the equation. This tests the null hypothesis. That means A0, which is null hypothesis, B1 is equals to 0. Large absolute T-value suggests rejecting the null hypothesis. The p-value measures the probability of observing such a T statistic if H0 were true. The composition of variation, this is the formula. TSS here measures total variation in Y. ESS measures variation explained by the model. ROSS measures unexplained variations, that is the residuals. What is R squared? This is the formula for calculating R squared. R squared measures the proportion of variation in Y explained by X. High R squared does not imply causality. Low R squared does not imply the model lacks economic importance. This is an example of income versus consumption. This is consumption, this is income. The fitted line illustrates the estimated marginal propensity to consume. This here is MPC. Then this is a demand curve. This is quantity demanded, this is price. So as price increases, the quantity demanded decreases, as you can see. This is a negative slope, consistent with the law of demand. This is a positive slope. Because here, as income increases, consumption also what increases. This fitted line illustrates I already said this before. Now let's look at interpreting the slope economically. Always interpret magnitude, directions, and units. Distinguish statistical significance from economic significance. A statistically significant effect may still be economically small. True. Elasticity approximation in level model. Now, let's look at elasticity. Is not equal to B1 times X over Y at a specific point. Elasticity measures percentage responsiveness. For constant elasticity, log models are preferred. Now, let's look at correlation versus causation. Regression captures association, but not automatically causation. Heterogeneity invalidates causal interpretation. Causal inference requires stronger assumptions or research designs. Now, by way of conclusion, um, we have learned what it means to have simple linear regression and we have looked at interpreting the slope economically. We have looked at correlation. We have looked at some diagrams. That will be all for module 2. We'll be going to module 3 now. See you in the next module.